Hello everyone. So actually this lecture was basically prepared for my students in SRM University, Sikkim. Due to this COVID-19, we are having this complete lockdown. So all the university, colleges, schools are all shut down. So that's why I'm making this a tutorial. So first we would like to do is magnetostatics. So before directly moving into magnetostatics, let's have a brief or a short revision of what we had in our electrostatics. In electrostatics, what we study is the property of a charge at rest. Now, in electrostatic, usually what we do is, suppose we have a positively charged particle, then it will have its fields going outward, and it's negatively charged, then it will come inward. So that's it. So we study the different properties, like what will happen if two charges are placed next to each other and find a electric field at this point, let's say at P, and we used to do it by the vector sum experience on this due to these two charges. Let's say it has a field E1 and it has E2. Then the total electric field at that point will be given by a vector sum of basically E1 and E2. E1 and E2. E2. So suppose if we place a positive test charge over here, then what it will experience? Then it will experience certain kind of force due to these two charges which are sitting out here. So this will also be given by the vector sum of these two forces experienced at that by this test charge particle which is placed over here. Suppose let's say the force exerted by this first charge is F1 and by the second particle is F2. Then the total force will again be given by the vector sum of these two, F1 plus F2. And this was called something as a superposition theorem. So similarly, we can also find the scalar potential, which is basically given by just the sum of, because it's just a scalar. So this was the story in case of electrostatics. Now what will happen if this charge starts to move? Let's say we have an electron, and if it starts moving in this direction, then it will produce something called a current, which direction is opposite to the direction of a flow of electron. So it was first noticed by Oersted that this moving charge or a current carrying conductor produces something called a magnetic field. So how he did it is, he placed a compass next to this current carrying conductor, and what he saw was there was some kind of deflection towards the left over here when the current carrying conductor, or the current is moving in this direction from down to up. Then the deflection was towards your left side. So this was the first evidence that your moving charge or current produces a magnetic field. So now how to find this direction of this magnetic field? So the direction of magnetic field is given by this concentric kind of circle. So in a straight isolated conductor carrying current, the magnetic field is circular and concentric with the conductor. So this is a conductor and it is concentric around this region, with the center being the conductor. And now either this direction can be in this anti-clockwise or in the clockwise direction. Now how to get this direction? Now this is given by something called a right hand collapse rule, which tells you if you collapse this conductor, or if you hold this conductor with your thumb pointing at the direction of your current, then the other finger, which is curling, will give you what? The direction of a magnetic field intensity over here in this direction. As the conductor is carrying current in this direction towards the up, then your thumb will be in this direction, then your finger will be wrapped over here. So the direction of the magnetic field will be anti-clockwise in this direction. Now how to see that? Now let's say this was a thumb and you grabbed it like this, and this was a current carrying conductor, and this is wrapping in this direction, so that's why the direction becomes anti-clockwise. So that is how you get the direction of your magnetic field. Now the next thing is, what will happen if we pass an electron in a magnetic field? Suppose this is a direction of a magnetic field. It is going inward from this base or inward from the screen, which is at the negative x-axis. This is a positive x-axis, so it is moving inward, so it is at the negative x-axis. Now next what we do is we shoot an electron from here in this direction. We shoot an electron which is coming, let's say, from this direction, and it enters this magnetic field. The electron is moving from here right to left, which is again at a negative y-axis, in the negative y direction. So the current will be produced on your positive y, because the electron is moving towards the left, so the current direction will be on your towards your positive y-axis. So again this will be a direction of your current. So it was noticed that this electrons get deflected. It get deflected either on this direction or on this direction. So this electron will experience certain kind of force, because this moving electron produces some kind of magnetic field. So this will also interact with this field which is already sitting over here. So that's why it will experience certain kind of force. So it will basically get deflected on your positive z-axis. So the force of a moving charge was given as force is equals to Q times V cross of B. Basically the cross product of this velocity and your magnetic field. Now because it has either it can go towards this positive side or in the negative side. Now how to find this direction? Now before moving to that, first I'd like to have a definition of B. What is B? Now we have force is given by Q V cross of B. Now the magnitude of B is given by Q V B sin theta. So basically at this B will be given by this as we move this to your left hand side. So the SI unit is force is Newton, and QV will give you what? Ampere meter, because Q times Q by T will give you current, charge per time will give you current, this will give you ampere, and the meter is sitting over here, so that will give you meter in inverse. So sin theta does not have any dimension, so the dimension of your magnetic field intensity is, or magnetic field induction is Newton per meter per ampere. So SI unit is said to be Tesla. So the magnetic field induction at a point is said to be 1 Tesla. If 1 coulomb of charge is moving with a velocity of 1 meter per second at right angle, so that if it moves to a right angle, your sin theta basically becomes 1 at right angle to the magnetic field induction field. Magnetic field induction field at that point experience a 1 Newton force.